Though we defined the GCD of two integers a and b, not both 0, we didn't clearly mention that why GCD should definitely exist. And of course, we have seen that when we are taking a and b to be both 0, GCD cannot exist. Now we will see that why we are saying that GCD of two integers a and b, where one of them at least is non-zero, will definitely exist. Now we are going to see why GCD of two integers a and b exists, provided that ab is not equal to 0. AB is not equal to 0 means ordered pair AB not equal to 0, 0. Not that ordered pair AB will become 0, 0 if and only if A equal to 0 and B equal to 0. If one of them is non-zero, ordered pair AB cannot be equal to 0, 0. So we are assuming that at least one of them is non-zero. So now we consider the set of all divisors of A. So can we say that A definitely will have at least one positive divisor? That's guaranteed because we know that the integer 1, the natural number 1, divides any other integer. Since 1 divides A and 1 divides B, we have 1 belongs to the set of all divisors of A, 1 belongs to the set of all divisors of B, and therefore 1 definitely belongs to the set of all common divisors of A and B. Therefore, this set is not empty. That's guaranteed. So we have the set of all common divisors of A and B not empty. Therefore, what is the least possibility for GCD then? GCD is going to be, according to our definition, it is the largest common divisor of A and B, and 1 is definitely there. Therefore, largest divisor cannot be anything less than 1. So GCD is going to be greater than or equal to 1. Therefore, if D equal to GCD of AB, then D is going to be greater than or equal to 1. This is guaranteed. Now the only thing we have to make sure is that D is not increasing indefinitely. That means there must be some bound for D so that we can stop at some point and say that, okay, we have done. This is the GCD of A and B. So that is actually guaranteed using the following property of divisibility. We proved previously that if A and B, instead of A and B, we will use some other symbol. If M and N are positive integers, and if M divides N, then we know that M is less than or equal to N. This is something we have already established. That means any positive divisor of another positive integer must be less than or equal to the second positive integer. Therefore, if we have CAB, the set of all positive divisors, if you consider CAB to be the set of all positive divisors of A and B, every element in CAB must be dividing A. So we will write it like this. So if some C belongs to CAB, C greater than 0, and if C divides A, then C must be less than or equal to A. Now, C divides B, then C must be less than or equal to B also. So the set CAB, how many integers can be there maximum? So if D is equal to GCD AB, then D divides A and D divides B, and so we have even previously observed that then D is less than or equal to A, D is less than or equal to B, and so D is less than or equal to minimum of AB. So we cannot in fact use this if this is enough, because we don't know whether GCD exists or not, so we will remove this. If D divides A and D divides B, then D is less than or equal to A. D is here also D is less than or equal to B implies D is less than or equal to minimum of AB. Therefore, so how many elements can be there maximum? Instead of a positive divisors, if we consider, then the starting element is going to be 1. Next element can be something greater than 1. Next element can be something greater than 1. So maximum there can be A number of elements or B number of elements. So basically it's going to be a finite set. So CAB, the set of all positive divisors of A and B, positive common divisors of A and B is a finite non-empty set. So it's non-empty because 1 is definitely there. It's finite because it can have maximum of minimum of A and B. For example, suppose that we are considering A to be equal to 10 and B to be equal to 15, then the set of common divisors of A and B can contain at most 10 elements. So if we have 10 elements, we can just start from 1 and we can locate the largest among these 10 elements since it's a finite set. Therefore, we can find largest in the set of all positive common divisors of A and B. So we can find the largest because it's a finite set. See, if this is not a finite set, it may not be always possible to find the largest element. It is not a finite set. In fact, it is not going to be possible to find the largest element. For example, suppose we are considering the set of all even positive integers. So we are starting with 2, we have 4, we have 6, etc. But we can never reach a maximum element. But on the other hand, suppose that we have elements like C1 positive, C2, C3, C4, etc. up to some Ck, then we can definitely check which one of them is going to be the largest. Because we can compare each and every element and we can locate the largest element from a finite set. So we can find the largest set of all positive common divisors because there can be at most minimum of A comma B elements in that set. So GCD AB exists. Not that this argument fails in the case of A and B both become equal to 0, because when we take A and B both to be equal to 0, then the set of all common divisors of A and B is nothing but it's a set of all natural numbers, and that is not a finite set. Therefore, we cannot find the maximum from that set. That's why our argument fails in the case when we have A, B both equal to 0. So this guarantees the existence of GCD when at least one of them is non-zero. We have observed some properties that the GCD actually satisfies. Some of them are GCD of A and B is sign independent. That means if we take GCD of A and B, or if we take GCD of A and minus B, or if we take GCD of minus A and B, or if we take GCD of minus A minus B, all are going to be the same, because whenever we have a C dividing A, we will have C dividing minus A also. Therefore, set of all common divisors or set of all divisors of A and minus A are exactly the same. Set of all divisors of B and minus B are the same. Therefore, the set of all common divisors of A and B, or A minus B, or minus AB, or minus A minus B, whatever we take, they are all going to be the same. That's why we say that GCD is sign independent. It does not depend on the sign of A and B. It can be positive, it can be negative. So most of the times, instead of taking A to be negative or A to be positive, we most of the times assume that A and B, instead of that, we consider modulus of A and modulus of B, and we observe that GCD of AB is the same as GCD of modulus of A, modulus of B. One more important property that we can observe quickly is that GCD of A and B is, or GCD of AB is same as GCD of BA. This is because if we consider the set of all divisors of A, CA, set of all not CA, we call it as DA. set of all divisors of B, DB, then we are taking DA intersection DB for finding the GCD of A and B. But not that intersection of two sets can be taken in either order. Intersection of DA and DB, that means DA intersection DB is the same as DB intersection DA. Therefore, GCD of AB and GCD of BA are exactly the same. There is no difference at all. We are going to see some more interesting properties of GCD now, especially what happens if we take A and B to be two prime numbers. What happens if we take A and B to be two integers very close to each other? Very close to each other means that if they are equal, then we have already observed that GCD of A and B is going to be equal to modulus of A or modulus of B when A and B are both equal. Next property we are going to observe is what happens when we take A, B both to be prime numbers. We know that if we take both the numbers to be the same, then the GCD is going to be equal to that number itself. So we take two distinct primes. Suppose P1, P2 primes and P1 not equal to P2. So the question is this. What is GCD of P1 and P2? So the answer to this question quickly follows from observing one fact. What are the divisors of P1? Divisors of P1 are nothing but 1 and P1. Divisors of P2 are nothing but 1 and P2. So common divisor, if we take P1, P2, then it's going to be definitely 1 there. Now P1 is not equal to P2. Therefore, P1 and P2 we cannot include. Therefore, other than 1, there are no other common divisors. So we remove this. This is the only common divisor if P1 and P2 are different. Therefore, GCD of P1, P2 is going to be equal to 1. So the observation is this. If we have two distinct primes, then their GCD is going to be equal to 1. Now we are going to make a slightly different definition using this property. We have two distinct primes, then GCD 1. If two numbers A and B have GCD equal to 1, we cannot say that they are prime because, for example, if we consider or we make a question here, if GCD of AB equal to 1, can we say that A and B are distinct primes? Note that we observed previously that if A and B are distinct primes, P1 and P2, then GCD is going to be equal to 1. Now the question is the converse. If GCD equal to 1, can we say that they are distinct primes? So if we carefully look at some numbers, we can easily find out the answer. For example, suppose that we are taking 2 and 3. 2 and 3 are both primes, so this question is not going to be correct there because 2 and 3 definitely they are distinct primes and therefore the GCD is already 1. Now instead of that 2 and 4, okay, we cannot take that. 2 and 5 GCD is 1, they are both primes. Now 2 and 6, okay, they are both GCD is not equal to 1, so we cannot take them also. 2 and 7, they are primes, so GCD is 1. 2 and 8, GCD is not 1. 2 and 9, okay. Now if we look at 2 and 9, 2 is of course a prime, but 9 is not a prime. But GCD is still 1. GCD of 2, 9. Because we know that divisors of 2 are 1 and 2. And divisors of 9 are 1, 3 and 9. So common divisors, there is only one common divisor, that's 1. So GCD is 1. But 9 not a prime. Therefore, the statement that GCD of AB equal to 1 does not guarantee that that these two numbers are actually distinct primes. But now we are going to make a slightly different definition from this. If GCD of two numbers is equal to 1, we call those two numbers as relatively prime numbers, or we say that those two numbers are co-prime to each other. So the definition is the following. If AB natural numbers such that GCD AB equal to 1, then A and B are said to be relatively prime or co-prime to each other. We already have one example. 2, 9, they are relatively prime or they are co-prime to each other. And of course, if you take two distinct primes, the GCD is already 1. We have already seen that. Therefore, if you take two distinct prime numbers, they are relatively prime. But if we take relatively prime numbers, they are not going to be actual primes. There can be cases where they are not actually primes, but they have some other indication. 2, 9 we have seen, and if we go further, then 4, 9 also we can take. Neither of them are primes. Example 2, 9 is a possibility. These are relatively prime. Next is 4, 9. That's a possibility. And 2, 3 is of course there. They are all relatively prime pair of numbers. Now we will see an interesting question. Two consecutive integers are always going to be relatively prime. N and n plus 1, two consecutive integers, are relatively prime. Prove this. We know that 1 is definitely a divisor of n and n plus 1, and therefore 1 is a common divisor. So 1 divides n and 1 divides n plus 1. Now let d be a natural number such that d divides n and d divides n plus 1. So if d divides n and d divides n plus 1, just recall the fact that if c divides a and c divides b, then c divides alpha a plus beta b for any alpha beta integer. That means common divisor of a and b will always divide any linear combination of a and b. So if we in the place of c we have d here, d dividing n and d dividing n plus 1. So if you put alpha equal to minus 1 and beta equal to 1, then d divides minus 1 into n plus 1 into n plus 1. That is, but what is this? This is n plus 1 minus n. D divides 1. But d is a natural number and d divides n. D divides 1. So what is the only natural number dividing 1? 1 itself. Therefore, since d belongs to n and d divides 1, 1 has only one positive divisor, that's 1 itself. D equal to 1. So that means that only one common divisor is there for n and n plus 1 in the set of full natural numbers, that is 1. Therefore, GCD of n plus 1 equal to 1, or n and n plus 1 are co-prime to each other.